and CO2. So certainly didn't want to revisit those, but critical raw materials is something that overlaps and fits in the same box in a number of ways, because we're talking about stuff that is vital to the way we live in today's society, but it's also something that's potentially under threat in terms of the way we are progressing and developing. And whatever James has done with this, it doesn't seem to lend itself to moving beyond slide 1.
Oh, how about pressing page down?
I've pressed page down, I've pressed page left, page right.
It just swaps you onto PowerPoint rather than WebEx. Yeah.
Right, that looks better. So critical raw materials. That was it. So what is a critical raw material? It's something that's economically and strategically important, but has a high risk associated with the supply, and there can be various reasons for that. So there are some materials that have no viable substitutes, and there are some where consumer countries are dependent on imports, or there are some where there are very few options about where you can get it from. And these can be materials that we use directly or indirectly. And there are certain critical materials, which is the bullseye in this target, which are deemed to be critical. There are others on the periphery of that are on what we call a watch list. And both in the UK, the EU, the United States, elsewhere in the world, different nations, different regions have their own lists. Not surprisingly, those lists look almost identical, not quite identical. I think there'd be something a bit strange if the list looked completely different. So the EU list and the UK list look pretty similar. The UK has its own list, which has the same things on it, but the Americans, being a wee bit more paranoid, choose to have a slightly longer list. And what's on there is what you'd say were the usual suspects. So, lining it up and looking at the commonality there, you've got groups of materials that are used in electronics. You've got rare earths that are used in magnetic things, so they're important for motors, for power generation, etc., etc. You've got some precious metals, and you've also got some other things that are maybe not immediately obvious. So you might not expect to see natural graphite in there, but graphite isn't as abundant a material as people believe. But whilst we all worry about the anode in lithium-ion batteries, we forget that it has a graphite cathode as well, as do many other things. So some of the uses are displayed on the right-hand side here. You can read the list. I'm not going to go through the whole of it. So just looking at the first few, you've got things like gallium that are used in semiconductors and electronics, also photovoltaics. Then you've got the things like neodymium, dysprosium, etc., which are magnetic materials, which are very important. You've got things like platinum group metals that crop up in catalysts, fuel cell applications. You've got the things that go into lithium-ion batteries. Strangely enough, lithium isn't the most critical. We worry more about the things like cobalt or even the nickel that coexist with it. But it's an extensive list, and you see things in there that you might not immediately bring to mind, like titanium. We think of many uses of titanium, but where it becomes critical is roles in things like desalination, some of the medical uses. So we have a variety of them. If we look at the criticality in terms of society, where the criticality is assumed to be highest is the things which will cause us the most inconvenience if we can't do it. So in red up at the top, and the materials tend to be the rare earth and magnetic type materials that where we're doing the worrying, you'll see they link up with the technologies associated with power generation from wind, traction, electric motors. So basically, the stuff that keeps society moving and keeps the energy flowing. And then as we go down the list, we get into the electronics, the photovoltaics, which are still important, but I think we'd all worry more about whether we can keep the lights on than just how many PCBs we can afford to have. And where do they come from? This is a very busy graph showing showing where some of those critical materials come from. An awful lot, as evidenced by the big circle on the right-hand side, are either resources that are embodied in China or resources that are controlled by China. But we also have other areas of the world that play a critical role, and this brings us on to also think about there being different reasons for criticality. Another way of looking at that is to highlight certain countries and areas which have significant strategic importance in terms of our dependence on these materials. So China, you will see, has more than a dozen critical materials associated with it. Russia only one, but then you get other things like Brazil. One company in Brazil and one mine in Brazil controls 90% of the world's niobium, which is important both as an alloying element in structural metals and materials, but also in electronics. Now, we're not too bothered about niobium in terms of how much there is and is there enough to go around, but the fact that so much of it is controlled by a single organisation makes governments wary, because if that organisation should change hands, or if the Brazilian government should change to some completely different political complexion, then something of which there is plenty, but basically only a single source, becomes a source of worry to us. I'll talk about the Democratic Republic of Congo in a slide or two's time. And equally, South Africa controls a lot of the platinum group metals. In recent years, we've begun to talk about the BRIC economies. We used to talk about BRIC, and then we added the S for South Africa on the end, and it's now BRICS. But between the economies of Brazil, Russia, India, China, and South Africa, there is a large amount of control over some of the most significant materials for our society in the future. And the BRIC economies are now beginning to act as a trading group and developing policies for how they will control and market their strategic resources, which is also tied up with their plans for economic development. And I think morally we can't say too much against that, but we have to live with the consequences that will bring. And part of that means if there is significant dependence, what are we going to do about making our own economies in the UK, Europe, North America resilient to those effects? And there can also be other reasons why certain materials become critical. So tantalum and cobalt, an awful lot of the tantalum and cobalt around, what the quantity is, it's that ethically and morally, many Western nations and many companies and organisations within those countries do not wish to trade with the Democratic Republic of Congo because of its. So ethically and morally, many of us, or the organisations or nations that we work for, don't want to source their cobalt from the Democratic Republic of Congo because of its record on human rights, exploiting child labour, etc., etc. So for perfectly good reasons, we can find difficulties over supply, and we may also worry about who might be waiting in the wings to buy up the rights and minds and organisations in those parts of the world. Is it a static situation or is it developing? This slide is a United States view, which says that, well, today we have a small group of very critical things in the red corner, but looking over the next 10 years, that group is almost doubling in size. In terms of economic importance against supply risk, the cross at the top of the graphic there says the ones we really worry about are the magnetic rare earth materials, which are largely controlled in China and which are vital for motors to either make things go or for transforming wind power into electricity. And then the group in the middle, the germanium, gallium, etc. We're talking about the electronics sector. So the UK strategy says what we must do is accelerate UK domestic capabilities. Well, what do we have? We don't significantly have any mines with any of this stuff in them. We have some bits and pieces of lithium. We have one or two deposits of other materials. So the government would like us to rebuild our skills in mining and minerals, but we have to convince ourselves that we've got something to mine in the first place. As I say, there are some glimmers of hope, but it's certainly not going to address the majority of things on that list. But we carry out cost-cutting R&D to solve the challenges in supply chains, make better use of what we have. But it's this bit, increasing recovery, reuse and recycling and resource efficiency, which is going to help most. So in terms of development, it's getting the most efficiency out of the way we use these things, which links back to a talk that Graham gave a few months ago. But it's also about end-of-life recovery and reuse. And the UK view on how we would do that involves collaboration with international partners, enhancing international markets. So a lot of that's to do with trade and trading relationships. If we look at the EU strategy, it's sort of similar, but whereas the UK view was strong dependence on international trade and relationships, the EU strategy is rather more about trying to get as much internal control as possible and reduce the external reliance. So yes, they still need to strengthen ties through the WTO, etc., and fair trade agreements. But if there's a difference between the UK and the EU, it's that the EU is rather less constrained in terms of there is a little bit more internal resource. It's still vulnerable, but they'll do more about it. Something in the top right of the slide, I've put something that says Critical Raw Materials Act. That is one thing that the EU has brought in about 18 months ago. 18 months ago? No, just over a year ago. Critical Raw Materials Act, that we don't have an equivalent in the UK. And what the Critical Raw Materials Act does is remove some of the barriers and red tape that go around developing routes for recycling and reuse. So when it comes to recovery of critical raw materials from end-of-life waste, from lithium-ion batteries, etc., it's actually quite difficult to do the R&D because the regulatory framework over what you can do with waste and how easy it is to get hold of the permits and how long it takes you to get the authorizations is a significant barrier to some of the R&D. I might touch on that in a few slides' time on some of the things that we've done in that, showing how you process something from an ore, it's a lot easier to get the go-ahead than basically applying the same process but starting from something that's designated as a waste, like a lithium-ion battery. If you want to research lithium-ion battery recycling, it's easier to buy a load of new lithium-ion batteries because you're not restricted. If you take end-of-life ones, they're designated as waste. Yes, they are. But the EU has already foreseen this and put in place a Critical Raw Materials Act, which is designed to streamline the authorizations. Anyway, I've got a little bit ahead of myself as to thinking about what the solution might be. So we put up all these graphics saying these things are critical, etc. Do we really need to worry? Mr. McCorber used to say something will turn up. We used to worry an awful lot about when North Sea oil was going to run out, and then magically we always found some more. Is the same going to happen with critical raw materials? I'm not so sure. This graphic shows at the bottom in the green up to 2050 projected need for lithium. So the green and the colours below it cumulatively. But the brown lines and the yellow lines are referring to known resource and reserves. And, well, they don't match. Lithium maybe isn't the greatest example to choose because if push comes to shove, you can just drain the oceans and try and extract it from seawater and you'll find enough, but it'll cost you a ridiculous amount to try and do that. The next graph says something similar, but I won't dwell on it. However, numbers always have to be taken with a pinch of salt, particularly when we're talking about reserves of raw materials. And this refers to a forecast from 10 years ago about the number of lithium-ion battery gigafactories that were going to be required to satisfy demand in Europe. And, well, we're nowhere near 30, and current predictions would say we're not going to need anything like that amount. And that's for a couple of reasons. First, the demand hasn't grown at the expected rate, but also the efficiency of the devices and things that we're producing has increased. So the amounts needed are not as great. So this crystal ball gazing is difficult, but even though it's difficult, the trend is definitely upwards, and it's definitely quite sharply upwards. So I think we will be foolish to just take the macabre attitude and say something will turn up. Lithium currently is predominantly coming from Australia and Chile. There is a significant amount in Europe. Finland has something like 14% of the known reserves around the world, and has yet to really get cracking on exploiting that. In the UK, we're looking at deposits down in Cornwall, so Cornish lithium, green lithium have some potential, but in UK terms, that will be significant. In world terms, not so much so. If we think about lithium-ion batteries, then along with the lithium, we've got cobalt and manganese and nickel in the cathode. And as we mentioned, dependency for cobalt very much on somewhere where we're saying we will not do business. But I suppose the good news is the other 50% is distributed quite widely. So in terms of different options of supply, it's not so bad. But where these materials are critical, so what about exploration and finding new reserves? We will do that, we can do that, we are looking for that. But the trends over the last 100 years, and here I show graphs for copper, for gold, for silver. If I could find the data, you could look at many other materials. Are saying that yes, we find new deposits, but the trend lines are about how much of the stuff is there in the ore, and they are all pretty much that yes, we're finding more, but there isn't the concentration of material in it. So that's saying, yes, there is a problem that needs to be looked at. And again, crystal ball gazing is never going to be accurate. But if you say, well, the projections are that by 2050, in many cases, we're projecting needing 10 times as much as in this case, I've taken 2017 as a reference point because that was where I had data. Some of these things, there's not an awful lot of years of supply in. And surprisingly, the one that looks as if it would run out earliest is zinc, which isn't even on anybody's radar as a critical raw material. But just about any flat steel metal product has a galvanized coating on it, which is where a lot of the zinc goes. But we need to do something about these things, and history will probably tell us that some of these are unnecessary fears, but I don't think every single one of them will turn out to be an unnecessary fear. Hence, there's a lot of focus on recycling and reuse. So what are we looking at in the UK? We have people involved with titanium, not native UK titanium, but at least with processing in the UK. We have quite a lot going on in the lithium sphere and in this area. We have green lithium and Tees Valley lithium, interested in battery manufacture, lithium exploration and refining, and down in the southwest I've already talked about Cornish lithium. That being the same sort of geology that you have in Brittany and France, where the French are looking at pretty much the same sort of deposits. In Cornwall, we're also looking at beginning to re-exploit mines for tungsten and tin, which we'd given up on in the past, and varieties barium sulfite sulfate is another area of interest. So, why does this leave us with so few natural resources in the UK? We're not suddenly going to leap into mining all the stuff we need because we don't have it. But what we do have is industrial processes and their residues. And when you extract something in an industrial process, when you've taken away the stuff that you did want, by default, you've concentrated up the stuff that was left behind. And there are some interesting sources in those. So particularly in terms of ashes, we can find significantly increased groups of platinum group metals. This was particularly the case with coal ash, but we're not producing much coal ash these days. But there are other forms of ashes, and the concentrations of platinum group metals in some of these process ashes can actually be higher than in the geological ores from which the primary extraction takes place. So there's definite interest in trying to extract from ashes and ores, and other forms of waste, mine tailings, wastewaters, and industrial waste products like processed dust, filter cakes, historic slags, can give increasing concentrations of things that we do want. They can also give increasing concentration of things that we don't want, like naturally occurring radioactive materials. But that's a subject for another discussion. So, looking at historic wastes and extraction from wastes is definitely of interest for recovering some of these materials. If we're talking about looking for iron or aluminium, it would make absolutely no sense at all, because it's quite intensive and expensive processing. But if what you're looking for is a rare earth or a platinum group metal, it can be worth doing. So we've got the industrial process wastes. We've also got the wastes from end-of-life materials. So, typical example will be the printed circuit boards, which have valuable metals from the electronics point of view. Also, quite a lot of gold. The little traces in between that connect all the different components. A useless fact to take away tonight is that 7% of the world's gold is now tied up in electronics such as printed circuit boards. So if you think that most of your gold is in your wedding ring and a few trinkets, well, you'd be surprised how much is actually in your TV and your phone and so forth if you added all of those together. And that means it's worth seriously looking at how to extract those things at the end of life. And extraction of this sort of stuff can have significant similarities to the sort of techniques that we use for what was on the previous slide, extraction from either very lean ores or process wastes or dusts, in that it will tend to be a combination of smash it up, break it into small bits, sieve it, shake it, gravity separation, cycloic separation, followed by dissolve it in appropriate acids and solvents, followed by whatever chemical process is appropriate, resin, membrane separations, electrolysis, depending on the material. But that is a pretty generalized process schematic for how you would recover material from a lean ore. But it's also the process schematic for how you would approach recovery from some of these industrial waste or end-of-life materials. So shown in another way, ores and concentrates, due to separation, manufacture use, but but bringing in the end of life recovery. But then, why did I choose to talk about this today? I mean, I'm Alan Scholes from the Materials Processing Institute, so clearly it's I've got some interest in the game, and we've historically been associated with pyrometallurgy, which is the predominant route for extraction of bulk metals and materials, ores that are fairly rich in what they contain. Historically, we were not so interested in extracting the materials from leaner materials, leaner ores. But we first really started to get interested in this doing something, getting on for 10 years ago, which actually Peter, in a previous existence, probably had a hand in, because down at Scunthorpe, where I think he was working at the time, you sponsored a master's student looking at what could be done with a nuisance dust in the steel industry called kish. The blast furnace process for producing iron and steel makes carbon saturated iron. It takes several hours trundling around before it gets to the steel plant to be turned into steel. Some of the saturated carbon comes out of solution. You could claim it's a way of making graphene, but we don't go as far as saying that. But it comes out of solution by sort of first floating on the surface of the metal, and then the thermal currents sort of throw it up into the air, and you get this nuisance dust, which is called kish, which is basically a load of platelets of graphite with a bit of silica and other stuff contaminating it. And steel plants collected, and they were using it because it had a lot of carbon in it as recarburizer for the process. Well, recarburizer has a value of £100 a tonne or whatever. Graphite flakes for electrode quality have a value in excess of £3,000 per tonne. So if you can find a way of purifying it and cleaning it up, then it's worth taking a look at. So we started from looking at this MSc thesis sponsored by Scunthorpe, but looking at cleaning it up, and there's a schematic of what we did, but basically, yes, you can. And at the end of the day, if you want to have a look at some of those things, there's some bags of shiny graphite flakes which ultimately became electrode quality. And that sort of sparked our interest in getting into this hydrometallurgy and materials recovery way of doing things. Unfortunately, we're about to close all our blast furnaces, so this one ain't going to fly in the UK, but there's still a heck of a lot of blast furnaces around the world. But it illustrates the point, and there are some pretty pictures of purified graphite flakes. So that was what sparked our interest first. What is our interest at present? We've got various interests to do with lithium and end-of-life lithium-ion batteries. So there are some reprocessing plants for end-of-life lithium-ion batteries that are quite wasteful. They basically smash up the batteries and stick them into a pyrometallurgical route and melt the stuff. The wasteful part of that is you burn off the PCBs, so you have the slight nuisance value if you've got to deal with dioxins and various cyclic hydrocarbons that you'd rather not have. But lithium, being the type of metal that it is, that burns off, and you lose the lithium. You also burn off the graphite, but you do end up with the nickel and the cobalt and manganese all together in some alloy that you can get some value out of it. It's downcycling rather than recycling, but that's what's currently have. So the difference in our approach was we wanted to start by using green or greener solvents that would allow us to recover both the graphite and the lithium in the form of a carbonate before then going on to look at the nickel, cobalt and manganese. So that's one of our interests. Another one is when we consider the various ores that occur for primary extraction of lithium, the wonderfully named spodumene is one of the main ores of lithium, but this occurs in two mineralogical forms. One of which is quite active and amenable to extraction of the lithium, and the commoner form of it is pretty inactive. So we've been working on what you have to do to flip over the mineralogy from one form to the other to make it more processable. We've also been looking at, I wouldn't say the whole of the route for recovery of rare earth magnets. One part of the value chain in that is separation, and then before you can get to the point of reuse, you have to demagnetize what you've already got. And we have a rotary microwave assisted furnace that is part of the methodology we're using in that. And we talked a little bit about zinc. People have been looking at zinc for decades, but we're currently comparing three technologies for removal of zinc. One is pyrometallurgical, two are hydrometallurgical, and some pretty pictures there of some of the kit that we play with to do these things. So there's starting in the top right hand corner, we've got lab scale equipment. We've got a top blown rotary converter, which is a pyrometallurgical route for looking at extraction from process dust and fumes. The bottom left-hand corner is the rotary microwave-assisted kiln, and the top left is a pilot scale-up of the hydromet. Of course, we're not the only people in the UK doing these things. The Royal Mint are wondering what to do now that people are actually using less coins, and one of their new developments is that they're using their expertise in gold smelting to say, well, we can have a go at recovery and extraction from end-of-life electronics. Their way in, or their main interest, is around gold, but they're also trying to extract the other valuable metals as well. So. Right, you've probably heard enough of me for one day, so at that point I will finish just posing the question, well, what's next in terms of critical raw materials? Just pose the question of where haven't we looked? Deep sea nodules are known to contain a lot of interesting and rare materials. There's currently quite a debate raging between various nations as to how ethical or how ecologically acceptable it will be to mine these things. So some nations are taking the view, well, no, we should leave the seabed in peace, because there are a lot of rare species and things we don't fully understand yet, and others want to go hell for leather with extraction. And I think the UK is yet to really make its mind up which camp it falls into. So the main point was to really put some ideas there to just provoke some interesting debate. So I'll leave it at that.